And we're back. This is Mr. Beebe, and welcome to another fun day in honors chemistry. So last week we talked about the phase diagrams, and we talked specifically about the normal boiling point and normal freezing point when the pressure is normal, when it's a normal atmospheric pressure of 1 atmosphere. However, it is possible to change both the boiling point and freezing point by adding or dissolving a solute into a pure substance. So for example, adding salt to water. So these two properties are called colligative properties. And the one thing I want to point out is they depend on the number of the particles. So how many particles you're dissolving into that pure substance. Remember, solute is what's being dissolved, like salt or sugar. What happens, and we're going to look at phase diagrams, it raises the boiling point. So on the phase diagram, it shifts that liquid vapor line to higher temperatures, and then the opposite is true for the freezing point. It lowers it, it progresses that freezing point. Okay, so if you look at this phase diagram, so our normal freezing point of water, we know 1 atmospheric pressure, that normal freezing point is 0 degrees. However, when we add something to it, and you'll notice today on all of our sidewalks, we add salt to those sidewalks, and what happens, it lowers the freezing point. So now the freezing point is below 0, so it's less likely to freeze. Then the opposite is true for the boiling point of water. The boiling point of water is 100 degrees Celsius. Then if we add a solute to it to make it a solution, the boiling point gets shifted to the right, or shifts to a higher temperature, so boiling point elevation. Non-volatile solute, like sugar or salt, elevates the boiling point of the solvent. And normally for both of these, we will just talk about water as the solvent. Okay, and the formula for calculating how much the temperature changes is Kb, which is the specific boiling point elevation constant for that solvent. And you'll always be given this for water. Kb is 0.51 degrees Celsius times kilograms over moles. And then times molality, which remember is moles of solute over kilograms of solvent. So you'll notice these units should cancel, and you'll be left with units of degrees Celsius. The one thing you should remember is that the boiling point of pure water is 100 degrees. So when you're doing this calculation, you get your value for delta T. Then to get the new boiling point of the solution, you have to add that to 100. Now for the freezing point depression, it's lower than that of the pure solvent, and the formula is exactly the same, except instead of Kb, now it's Kf, the freezing point depression constant, instead of the boiling point depression constant. And Kf for water is 1.86, and you'll either see those units as degrees Celsius times kilograms over moles, or just as degrees Celsius over little m, the units for molality. Now the tricky part here is the freezing point of pure water is 0. So once you get your delta T value to get the new freezing point of that solution, so you have to take the freezing point of water, of pure water, 0 degrees Celsius, then subtract by that delta T value to get your new freezing point of the solution. And the reason why, when we're adding something to water, it freezes at a lower temperature. Normally, this is just pure water. So at 0 degrees Celsius, ice is in equilibrium with the liquid water, and this is the mixture containing a dissolved solute like salt, it interrupts that equilibrium, so it freezes at a lower temperature. Maybe even have seen salt trucks today, or walking down Brick Row, you will have seen salt, and that's the major reason why it melts the ice, so we're less likely to slip. And it's the same thing when you're adding antifreeze, which consists of the chemical ethylene glycol, to your car radiator, so it lowers the freezing point, so it is less likely to freeze. Now, just like you did in the lab today, there's differences between electrolytes and non-electrolytes. So electrolytes, things like salt, fully dissolve in water. They fully dissociate in water. So this Van't Hoff factor I calculates for that. It's the moles of particles in solution over the moles of solute dissolved. So for non-electrolytes, like methanol or sugar, I is always equal to 1. So that's true for any non-electrolyte, so any covalent compound, any molecular compound. However, I is not equal to 1 for ionic compounds since they dissociate and break apart in solution. So for example, something like salt, sodium chloride. When it dissociates, when it breaks apart, NaCl breaks apart into Na plus and Cl minus, so it breaks apart into 2 ions. Therefore, its Van't Hoff factor I equals 2. Same thing with KNO3, even though it contains a polyatomic ion, when KNO3, potassium nitrate, dissociates, it breaks apart or dissociates into K+, the potassium ion, and the nitrate ion, NO3. However, something like Na3PO4, when that dissociates, when that breaks apart, it breaks apart into 3 sodium ions and 1 phosphate ion. So that means it breaks apart into 4 different ions. So the Van't Hoff factor is 4. So we include that I, we include the Van't Hoff factor in each equation. So both for boiling point and freezing point, you have to make sure you multiply by I if you're working with an electrolyte solution. So for example, let's say you have a 0.57 molal glucose solution dissolved in water. And you want to know, okay, how much is that going to raise the boiling point and how much is that going to lower the freezing point? So for boiling point, we take Kb times the molality, and the Kb for water, which will be given to you, that constant, 0.51, and then times the molality, 0.57. So those units cancel. So the change in boiling point will be 0.29 degrees Celsius. However, that means the final boiling point, you have to add this to 100. So the final boiling point would be 100.29 degrees Celsius. And let's say instead it was 0.57 molal solution of NaCl. Now when we're calculating the change in boiling point, we have to take the Van't Hoff factor 2 times Kb times the molality. And now the change in boiling point of this would be 0.58. So the change in boiling point would be 0.58 degrees Celsius, meaning the final boiling point of this solution, to add 100, would be 100.58 degrees Celsius. Okay, now if we were trying to calculate the freezing point lowered by a 0.57 molal solution of glucose, so for the change in the freezing point, since it's glucose, since it's a non-electrolyte, we can ignore the Van't Hoff factor since it's 1. The Kf for water, 1.86 times the molality, 0.57. And so your change in freezing point is 1.06 degrees Celsius. However, that means your final freezing point, remember you have to take 0 minus that value, so that means the new freezing point of that water solution is negative 1.06 degrees Celsius. Now, if instead this was 0.57 molal solution of salt, you would have to multiply by 2, since salt NaCl breaks apart into 2 particles. So the Van 't Hoff factor is 2. So that means the change in freezing point would be 2.12 degrees Celsius, and the new freezing point would be negative 2.12 degrees Celsius. So on roads, normally we use salt, but sometimes you'll also use calcium chloride, CaC2, and sometimes that's more effective since the Van 't Hoff factor of calcium chloride is 3. All right, that's it for today. I will see you next time.